Today, we're going to talk about cluster analysis. Cluster analysis is an analytic technique for identifying naturally occurring groups within data across any number of measures made. If you look around online, you can probably find a lot of tutorials which will cover the nitty gritty details. This video will be a little different. Today, we're going to focus on the practical side, how to implement a cluster analysis for biomedical researchers. It won't cover every way to do a cluster analysis, but it will get at how to make key decisions when planning, what data to collect and use in the analysis, as well as how to process it, aware that there's usually strings attached when using real world data. We'll also include some tutorials in our software along the way to show you how it's done. To do all this will take some time, but I think it'll be worth your while. So grab that extra cup of coffee and settle in, and we'll get started. Cluster analysis is perhaps most easily understood by visuals. Take these hypothetical data, for example. When you look at the locations of where the data points are, you can visually tell there are a bunch of red points in the upper right, but most of the points are blue down along the bottom. Our eyes are designed to pick up on patterns. So in this case, it's easy, especially if we color code the points to make the cluster identities explicit. But what if we wanted to use a computer to figure out which points are red and which points are blue? The challenge is real world data usually aren't this obvious. For example, say you work in pediatrics like me. If you're in pediatrics, you might be doing a project looking at age. And if you're looking at age, you're probably restricted to a limited range of ages. And we usually round each age to the latest year. Point being, while age itself may exist as a fine grained continuum, the data we have are often pretty general, with only a few different years represented. As another example, you can think about Likert scales. So if we're rating an attitude from 1 to 7, there's only 7 possible response levels. And in many cases, people bunch up around 2 or 3 key responses. The idea of visually inspecting scatter plots for patterns seems like a good idea, but in practice, it just gets a bit complicated. It usually isn't as clear as we'd like. Fortunately, cluster analysis can help us navigate this. Let's return to that first scatter plot. To start, let's break down what's going through your head when you look at this chart and naturally sort out the groups between the red and the blue points. Our eyes naturally look for areas where there's a lot of data points, and we sort of look for approximate centers. Then we look around those centers to identify if there's a pattern. So, do all these points kind of look like a circle, or is it more like an ellipse, implying some amount of association? We can use this to help distinguish groups in the data. In a nutshell, that's all cluster analysis is doing. There are different algorithms that can accomplish this in different ways, but that's the common goal. First, the computer looks for where the distinct centers are in the data, which we generally call centroids. And then the algorithm will identify the dispersion of the data around those centroids. Finally, each individual is sorted into cluster groups based on how close the individual data points are to the centroid, as contextualized by the dispersion. Now that we've covered the main idea, let's start thinking about data processing, which is like 90% of what makes a cluster analysis successful. There's no one way to do this, but I like to use principal components analysis, a method I find especially practical for preparing data for cluster analysis. This can help rescale the variables to account for differences in how traits were measured, and also address some problems in the data, like missing data. Additionally, as mentioned before, raw data in biomedical research often doesn't show obvious patterns. So it's very possible that I will, or even the computer for that matter, we might have a hard time identifying the patterns based on the data alone. Principal components analysis can help simplify the data to highlight the most remarkable differences, even if the original data aren't entirely clear cut. Let's start with data cleaning, then we'll move on to principal components analysis next. Working in R, I'm going to assume that you've worked with R before at least once or twice. So we're not going to cover a lot of the basics. If you do need some information on how to get started in R, I'll put a link in the description to a video I made. You can also check out Google and YouTube, but we have a lot to cover, so let's get started. So this is a data set on people who have sepsis. Sepsis is an infection of the blood. It's unfortunately a very serious condition because if it can lead to like organ failure, and you also might not survive if you have sepsis. So we thought, well, what if we have people when they come into the ICU with sepsis and we looked at the characteristics of their blood? What's in their blood? What are their blood cells shaped like? Maybe that will tell us something about how they're responding to this septic infection. And then we can use that information to say who should we focus on, who needs to help manage their infection better, that kind of a thing. We also wanted to include age in this analysis because we think older people tend to respond to infections differently than younger people. And so the thought was that we can use all this to do a cluster analysis and identify groups of people based on their age and how their blood is responding to the infection. And we can use that to improve how we help people in the ICU. When we get the data, lab data are a little bit complicated. So this function will create a table of how much data are missing for each variable. And so age and role here, their age, only 2% are missing. 0.02 stands for 2%. So that's not surprising because most people have age somewhere in their chart. Really, I'm more worried about values like this PT and PTT. So if we have a value of 0.67, that means 67%. In other words, if we have 3 people in the data set, 2 of them don't have a PT lab, or this 80% for PTT lab, that means that if there's 5 people in the data set, 4 of them don't have any data. And that's a serious problem because it's probably not a mistake. If I'm really sick, my provider might order more labs for me. And if we only included people who had all of the labs available, we're no longer talking about all septic patients. We're really talking more about people who are like really, really sick and have all of the labs. This is important because that means I should probably drop PT and PTT from the analysis. I don't want to. It's not that I don't think it's important. It's more like I don't have a choice. I did not collect enough data on these labs, and I don't think I'm going to get a good result if I include it in the analysis. Another thing I'll need to think about is how much data are missing by individual. So this little bit here will tell us, let's go through each individual and calculate how much missing data they have across the 6 variables we have. Unfortunately, most of these people are 0% missing, 0 for 0%, which is a good sign. That means most people have most of the labs and their age recorded. However, the average is at about 8-9%, and the max here is at 1 for 100%. So there are some people with a lot of missing data. And that's going to be a problem because if I have a lot of missing data, I might not be able to include these people in the analysis. This little function here will say, all right, figure out who has 100% missing data. They have no data available, and tell me how many people there are. And fortunately, it looks like there's only one person who has no data available. So in this case, we're going to exclude that person from the analysis. Keep in mind, I don't want to do this. I would rather include everyone in the analysis because anyone with sepsis is relevant to the question I'm asking. However, if all we know is that you have sepsis and we don't know anything else about you, there's no way I can include you in the analysis. Not because I don't want to include you in the analysis, but because I have no other choice. It's okay that there's only one person missing, but if you had a larger value, you'd want to be cautious. You might say, I don't think I collected enough data. I might need to collect more data before I can proceed with this analysis. Okay, now that we're getting to the end of sort of basic data reading in stuff, now we'll want to save a couple objects for later. So this labs BU stands for backup. I want to save just the raw lab data as a reference point for later. We're going to come back to this. We're going to do some edits to the data. And so I want just like a standard backup to hold on to for later. This PCT OBS, that stands for percent observed. So the idea here is if it's a value of 1, that means we have 100% observed. we saw every single data point for these people. If we see a value of 83, that means 83% observed, so they were missing one variable. This is just a reference for how much information we have on each person. We'll talk about this more later. Getting into it, really, I'd like to know what the data are like. Now I know what data I can use, who has data available, what variables are appropriate to use, but I'd like to know what the data are like. So I'm going to use the psych package, specifically the describe function. This is really helpful. It gives you information on the average, standard deviation, the median for each variable in the analysis. It's also got the minimum and the maximum, all kinds of useful information. For assessing data and how to use it in cluster analysis, I actually focus, not everyone talks about these, but I like skew and kurtosis. What the heck would I like skew and kurtosis? Well, skew represents asymmetry in the data. Do we have all the data bunched up in one area, or is it like pretty symmetrical, spread out like a normal distribution? Same deal with kurtosis. Do we have some like really extreme values, or is it like most of the data are all in one place? And really, the reason this is helpful is because we can talk about what is typical. And so if we see a value like 2 or a value like 6, that kind of concerns me. This doesn't mean we have a data problem. It just means that there are extreme values in the data. And importantly, I should account for this in how I analyze the data, because otherwise the cluster analysis might pick up on something else than what I'm interested in. So let's do some box plots just to visualize this. I'm going to start with age just because it doesn't have a skew problem, just as like a simple example. So let's see how the distribution of age is. It looks like in the gray box, that's going to represent the middle 50% of the data. So most people are ages 50 to 70, but then these whiskers up and down here, that means what are like the variation in the data. So we got some people who are like in their 90s, some people who are like in their 20s. Most people, though, it's pretty evenly spread out across the whole typical human lifespan. So this is about, pretty evenly spread out. Compare now, let's look at lymphocytes. Lymphocytes have skew 2 and kurtosis a little bit under 6. Well, what does that look like if we plot that? As we see, we have values as low as 0 in here. And we have values that get up to like 2 pretty regularly, but most people are in the range of 0.5 to 1. And there's some people that are up around 3, closer to 4. This is what we talk about when we mean skew and kurtosis. The data are not symmetrical at all. There's some really wild values, even if most people are all in one area. Importantly, some people call these circles at the top, they'll call them outliers. I would not consider this an outlier because I expect this for lab data. You might be thinking, why would you expect that? Well, it actually makes some sense if you think about it. This is representing lymphocytes. Lymphocytes are a volume. How many lymphocytes are in the sample of blood? You cannot have less than 0 for volumes. In other words, you can't have a negative value. So point being, a lot of people have very small values of lymphocytes. That is to be expected because they don't have the worst infection. Some people have a very bad infection. Of course, there's no cap to how many lymphocytes you could have. So it makes sense that they would bunch up at the bottom, and some people have really high levels. This doesn't represent an outlier. This just means there's skew in the data. And that's not a problem, but it does mean we need to think about it and how we incorporate it into the analysis. So one way we can do this is with a log transformation. This is just a rule of thumb I tend to use. Other people might say something else, but I'd say if you see skew that's like above 1 or kurtosis that's greater than 4, you might want to think about a log transformation. A log transformation just means take the individual values and apply a natural log to them, which will bring the large values down a little bit and spread out the small values. Importantly, we cannot take the log of 0. It is undefined. And so we do need to be aware of that because for lymphocytes, we do have 2 people with a value of 0. Is this something you want to be careful about because you don't want to accidentally delete people with 0 values in the data? So it's an easy check. All we have to do is to say, well, if we only have a couple people in here, we know that the minimum value the device will record is 0.1. So we could put it at 0.05, halfway between 0 and 0.1. This works because there's only 2 people in that situation, but that's something you can think about as a way to deal with this problem. After we do that, now we've replaced all of our zeros with values that we can log transform. We can apply these log transformations. As we can see, skew and kurtosis for all of these is much closer to 0, which is better for the analysis. At this point now, we can move on to talking about next steps for data processing. Now that we have some sense of what data we want to use and think the measures made are suitable for inclusion in the analysis, now we can think about how to best highlight key group differences. A challenge in cluster analysis is scaling. Let's go back to that conceptual scatter plot. It's pretty clear looking at the data. Most of the variation for the red points and the blue points is in terms of the horizontal x-axis. Yes, there is some vertical variation, but there's more variation from left to right rather than up to down. This matters because if we have a discrepancy in the variation, whether it's our eyes or a fancy schmancy computer algorithm, it's going to be easier to tell differences in the data based on high variation in the x variable along the horizontal axis rather than the low variation in the y variable along the vertical axis, irrespective of which one contributes more meaningful information. As an example, to make it more concrete, it does not matter if you conceptualize time in terms of hours or minutes. However, in terms of raw data, there are a whole 60 minutes in just 1 hour. So it may be easier to see differences in minutes if we are not careful about how we scale the data. Additionally, let's say that you have a categorical measure, and that can be extremely distinguishing because it really represents something conceptual rather than a continuum. However, if we incorporate this using dummy codes as we often use to represent categorical groups, the scaling will go from 0, meaning not in the group, to 1, meaning part of the group. The concern is that an unintentional choice about scaling will mean giving priority to one measure over another, not because one is more relevant, just simply because there's a wider range of possible values present, which means that it's easier for the computer to pick up on the differences if there's a wider range of values possible. This is an advantage of principal component analysis. Principal component analysis rescales the data based on the variation in the data as well as the associations between the individual variables included in the analysis. By mathematically rotating the data in Cartesian space, the new transformed data can help to identify clearer patterns across all of the variables included in the analysis. That's a lot of abstract and mathy words in there. Let's take a look at some pictures to make it a little more explicit. Let's go back to that hypothetical scatter plot where we want to split up the red and the blue points. Looking at that chart, we can identify some patterns in the data. Outside of the differences in just overall averages, the blue points tend to have a positive association. So in other words, if the x variable is higher further to the right, then the y variable is also higher. It tends to be a little bit higher up. Suppose now that we drew a line through the blue points, representing the magnitude of this association. We could then use this line to rotate the entire chart clockwise, just down a little bit, so that the line in the middle of the blue points becomes the new x-axis along the bottom. I know it might seem silly to do something like this, but it actually makes it much easier to identify which points are red and which points are blue. If we draw a line in the middle of where the points are now, it isn't perfect, but we can pretty quickly separate out the red points above the line from the blue points below. This is what principal components analysis is doing on a basic mathematical level. By examining the associations and variation in the data, the analysis will identify what we call a linear projection. And that just means the dashed line from before that represented the association we saw. We can use that linear projection to rotate the location of the x and y axes. And this is incredibly helpful because it simplifies the problem of identifying groups in the data. If the red points and blue points are more distinct to begin with, that means it's less likely that the computer makes a mistake when identifying which groups are corresponding to the two colors that we put on the plot. In terms of logistics, you can look online for more information about the details of the math stat that underpins this, but the practical side is pretty simple to implement. Based on the correlations between the individual data points, we're going to create a set of weights that gives us information about how much each individual variable provides information about the linear projection. Which values are most important, which values are less important. More specifically, if we take the value of each weight and multiply one person's data by each of their individual data points and add those values together, so weight times x1 plus weight times x2 plus weight times x3, that corresponds to the rotated x and y axes like we just did a minute ago. You can check out a few ways we write out the equations if you like, but really, most of the details we can handle pretty easily within R. I like to use matrix multiplication, which is a very flexible and simple way to multiply and add up a bunch of values all at once for a whole matrix of data. But that's really not the important part. What's much more important is just understanding the process that underpins this. All we're doing is taking some weights that represent which variables were most meaningful, multiplying it by the raw data points, adding them together. Let's head back over to R to see how to make it happen. The first thing we want to do with data processing is calculate z-scores. Z-scores just means taking each individual observation and subtracting from it the grand mean, or the overall average, and dividing by the standard deviation. This just means that everything has the same scaling. So a value of 0 means it's at the overall average. A value of 1 means it's one standard deviation above average, and a value of -1 means it's one standard deviation below average. And that's really the whole point of doing this, is that it helps to account for the reality that we measure things on different scales. A dummy code of 0 and 1 is very different than, if we have a lab value that can get very, very high. And we want it to all be in the same rough units in terms of what a value of 0 represents, or a value of 1 represents, a value of 2 represents. This little function here is what's called a for loop. And so what's going to do is it's going to say, let's go through all the labs and subtract from each lab the average for it. And then we'll divide by the standard deviation. That's why it's a for loop, because it's saying go through all the columns from 1 to however many columns there are and change the value of p. And this variable will shift it each time, so that way we represent each column in the analysis. Now that we've run that, we can start doing the analysis. So principal components analysis is an analysis of the correlation matrix. So which variables are highly correlated with one another. High values mean high values for both variables, or if there might be a negative correlation, so a high value on one variable means a low value on the other. The core function can do that. So we're going to do our correlation across all of the labs. In this case, we have some missing data, so I'm going to specify to use the pairwise complete observations. That just means use however much data we can for each pair of variables. Again, this isn't a perfect solution to missing data, but it will help us use the amount of information we have, as long as you don't have a large and systematic problem with missing data. At this point, you can look at the correlation matrix and, say what's correlated with what, but really this is like too much information. What we want out of principal components analysis is a summary of what's going on here. And we can use this print_comp meaning principal components. We're going to say, all right, give us the principal components for the correlation matrix. And really what I'm interested in are what we call the weights, or loadings, that represent how much does each individual variable provide information about the same linear projection. So if there's one underlying trait representing inflammation response, how does age contribute? How does RDW contribute? How does MCV contribute? When we do this, we actually can have as many principal components in here as there are variables in the analysis. But that is too much information. We aren't looking to represent everything. Really, we just want to look at what we think is most relevant. So in this case, I'm just going to look at the very first principal component because I think this is the most important principal component. I think there's one trait of inflammation response that should represent one linear projection. How does age and all the characteristics of your blood all come together to represent the same information about how you're responding to the infection? So if I choose the loadings entry within the principal components object and I specify specifically the first one, it'll give me a value for the weights for that specific principal component I want to incorporate in the analysis. I'll save that as an object called W so that we've got all of these pieces of information here. This is when we talk about rotating the matrix, this is what we're doing. If we take an individual's age scaled as a z-score and multiply it by 0.4, and then their RDW scaled as a z-score and multiply it by 0.6, and so on and so forth, multiply each individual value times these weights, that will give us that matrix rotation we were looking for that represents information about who is more distinct from whom. So I'm going to do a last little edit here. I'm going to make a new object that's called labs z. And this is the same labs object we had before, but we're going to do one little difference here. So we're using a for loop again. So we're going to go through all the columns. And each time, if there is a missing value, so the lab value for this variable is missing, is.na, it's missing, then we'll plug in a value of 0. In other words, impute the grand mean for that group, the average overall for that whole variable. Otherwise, we'll keep it as it is. And that's the whole point here. The problem with principal components analysis is that if we have a missing value, what do we multiply these weights by? And what I'm proposing is that we actually multiply it by a value of 0. We're just going to ignore that trait. That might seem like a little problematic, but it actually makes some sense. Because really what we're saying is that each of these traits contributes to the same underlying function of infection response. How does age contribute to our understanding of infection response? How does platelets contribute to our understanding of infection response? If I didn't have a lab value for platelets or whatever it is, I'm just going to essentially keep that information out. We'll talk about this a little bit more in a second, but there's also a little bit of arithmetic we can do to help address this in more detail. But for now, we're just going to drop out all of those missing values and fill them in with 0 for the overall average for everybody. Last thing we need to do is do that multiplication. So multiply your age times each of these weights. Multiply RDW by the weight. Multiply MCV by the weight. And we could do this one at a time, and it'd be a time-consuming process. Fortunately, there's a real easy way to do this. It's with matrix multiplication. So since we saved this as a matrix with all the raw data, and this is also a matrix with the weights, we can say, let's just multiply the two matrices. We don't need to obsess over this. But that's what matrix multiplication does. It says multiply all the entries together and add them all up. So if we do this little function here, it's going to make all that math that would be really complicated really easy. And so now everyone has a single value corresponding to how severe of an inflammation response they have based on all the traits in the analysis, based on how the traits are correlated with one another. Additionally, if we wanted to see these PCA scores, as we'll call them, we can just do a little histogram. And if we look at this histogram, this is why it's helpful. It's because now we've sorted people out. It looks like there's some people who are a little bit lower than average, some people who are a little bit above average, but there's also a lot more variation in the above average area. That's really the whole point, is that then we can analyze this cluster analysis. And I don't know how many groups we'll find, but we'll probably find a group of people over here who have one type of inflammation response, and another group of people who have this type of inflammation response. And that's the whole point, to say we want to sort out the different groups of people. And rather than having a bunch of data that don't show clear trends, we might show clearer trends by pre-processing it with principal components analysis, just like this, where there's already clearly two groups, and there might even be some more if we looked at this chart in a little bit more fine-grained detail. That's the idea. We still need to talk a bit more about missing data, but this is what will get us started to do the analysis. This is the basic starting point for using principal components analysis in pre-processing data for cluster analysis. If you have no missing data, you could skip this next bit. But honestly, part of the reason I find principal components analysis so darn practical is because there's a simple edit to the analysis that will make the results much more capable of handling missing data when you get to the final cluster analysis. So, what happens if there are data missing? That's the good news. Principal components analysis is already remarkably resilient when it comes to missing data. Because the results are based on the linear projections in Cartesian space corresponding to patterns across all the data, if an individual is missing one or two data points, it won't excessively hinder the results. Put it another way, no one observation is essential for determining the results. Rather, it is the combinations of observations that constitute the principal component scores. So, as long as most people have a good bit of data, we can get pretty close to the right values, even if some people are missing a data point or two. This is, however, one last data processing step that we need to attend to get good results. So when we were working in R, we imputed a value of 0 for any missing values. That's a simple way to ensure everybody has a principal component score. The problem is that this will imply some changes to the underlying arithmetic. Because these principal component scores are defined as multiplying the original data points by the linear projection weights and adding them all together, that implies that the scores for individuals with missing values will be closer to 0 than they should be. Why? Well, because the average across everybody has to be at 0 by mathematical definition. So, individuals with missing values will have fewer opportunities to obtain principal component scores that are further from 0, per the definition of basic addition. Here's a visual to make it more concrete. And let's say we have 5 variables in an analysis, and we use principal components analysis to create individual scores across those 5 variables. This is a plot of how many people tended to have which scores. So the x-axis is the principal component score z, calculated using the 5 weights, scaling information across the 5 variables. And the y-axis is the percentage of patients who will have that individual score. And in this case, looks like most people have slight positive values, but is a smaller group of people who have negative values, and there's also some more spread in the negative values than the positive values. Great. Suppose now we put some lines on here for one specific individual. The black vertical line on the left represents the true score some individual should have, which shows up right at a value of -3. However, this individual was missing a data point. They only had 4 variables observed rather than the 5 they should have. Let's say that missing data observation, when multiplied by the principal component weight, would add -0.6 to their score. Because of that, the vertical red line represents the observed principal component score, coming in a little bit closer to 0 than it should, only at -2.4. This is the problem I'm talking about. Principal components analysis is a practical way to distinguish groups of individuals across the primary data, aware that all data have limitations. But if there are missing values and we impute a value of 0 for them, that means we may have some individuals with missing values that result in principal component scores too close to 0 because of it. Fortunately, there's a simple solution. What if we rescaled the principal component scores based on how many data points were available for each individual? So the original scaling went from about -6 to +4. But if we divide that by 5 for the 5 variables in the analysis, this is what the new density plot looks like. It's pretty much the same. Only real difference is the values on the x-axis, which now go from about -1 to +0.5. This is why it helps to take this step. Let's draw on again that black line where our individuals should be. Originally, their true principal component score should have been -3, so -3 divided by 5 gives us -0.6. Great. However, this individual was missing a data point, so we only observed their principal component score at -2.4. Because they were missing this data point, we won't divide by 5, instead we'll divide by 4, because there are only 4 data points available for this individual. So let's see what happens. -2.4 divided by 4, that gives us Hey, look at that, negative zero point 0.6. And if we put that dashed vertical line back on, this time it lines up exactly with the black vertical line. And that's why this method works for missing data. Even if we don't have all the data points for everybody, the amount of information is scaled up so that the final values are proportional to the amount of information we have. Keep in mind, this only works if it passes the sniff test. If there's a lot of missing data, or there's like a systematic reason some people are missing different data, no amount of fancy schmancy analytics can overcome that problem. Some people call this the missing at random assumption. I just call it common sense. If you've got a gaping wound, don't expect a band aid to do much to help. However, if you have small amounts of missing data here and there across many individuals, pre processing data with principal components analysis like this can be a very practical solution. That's it. Data are finally ready for cluster analysis. At this point, let's go back over to R to look at how to implement these last steps, as well as look at how to do the actual cluster analysis itself. So what I'm proposing is that we can just take our z-scores that we calculated representing where things are in principal component space, which presumably represents an underlying inflammation response, but then we can just rescale it to how much data was available on each individual. That's actually simpler than it sounds to implement. If you recall way back when, we actually saved an object for how much data was available. So 1 represents 100% observed, 83 represents 83% data were observed, and that's why we saved that. If we take the amount of data that was available for each individual and multiply it by this z-score, we'll get exactly what we need, a rescaled value corresponding to how much data was available. We'll go ahead and do that real quick. It's just simple multiplication because we already have the data set up the way we need it to. Now we can actually do the cluster analysis to compare different groups of people. First, we'll need the package called cluster. Also, too, I wrote some functions just to make this really easy to do, and I'll put this in the description with the rest of the code here. This will read all of the functions that I'm going to use because some of these are custom functions I wrote to make cluster analysis as easy as possible. So you can run that and use the functions on your own. The first step we'll need to do cluster analysis is create the distance matrix. What is the distance matrix? Well, that's saying, well, what if we compared everybody to everybody else? So individual 1 compared to individual 2, individual 2 compared to individual 3, also individual 1 compared to individual 3. You might be thinking, this is way too much. That's really the whole idea here, and why we're not going to look at the distance matrix too much. It's trying to say, what if we compare everybody to everyone else? And based on that information, we can give that to a computer algorithm. Because looking at every pair of individuals would be too much for a person like you and me. But for a computer, it can go through that and say which groups of individuals have small distances, i.e., data that are really close together. They all have negative values on this z-score. In which the individuals have, positive values on the z-score. They're more similar to one another. And so that's what this is going to do. This is called Ward's method. There's different ways you can do it. I like Ward's method just because I think it makes sense. What Ward's method is doing is saying, let's try to identify cluster groups such that the averages are as distinct as possible, but the variation within the same group is as small as possible. There's different ways, you can look online for more information about different algorithms. So that's the one I like because I just think that makes sense. And we can accomplish that using the hclust function. We give it a metric of distance. We tell it what method we'd like, and that will create different groups. Really, though, if we just ran this hclust function, there'd be too much information. It gives you a lot of output. I like to start with a visual just because I'm a visual person. So I'm going to do this plot function around the hclust function. This will create for us what is called a dendrogram. What the heck is a dendrogram? Well, the idea here is say, what if at the bottom, I know it looks a little bit overwhelming. That's just because we have a large data set. At the bottom, we have a unique individual. So every single one of these lines at the very bottom is a unique person in the data set. It's also why all these numbers are jumbled up together because it's trying to label each and every person in the data set. Obviously, there's too many people to do that well. However, the real value here is looking at how it looks as we go up the chart. So as we go up, everyone's their own unique individual person, a cluster of one. We're going to start grouping people together based on people who are pretty similar together. And we're going to keep grouping individuals, then grouping clusters together until we get all the way up to the top here, where it's like we're all one big happy family. No one is different from anybody else. And that's really the whole point, is to say, well, what if we use this to inform our conclusions and interpretation about what the cluster analysis represents? So maybe we could scale the height of these individual lines to how different or similar the groups of people put together are. So down at the bottom, these bars, the vertical height is really low. These bars are really short. That just means we're grouping similar people together. But as we get higher up, these lines start to get a lot taller. And that means that maybe lumping these people together wasn't a good idea. Maybe that might be like putting apples in with oranges. That's the whole point. There's no one way to do this, but we can pick and choose how many clusters to look at based on the information in here. So when I see this, I see at least one, two islands in here. But you could say there's maybe three, or 1, 2, 3, 4, 5, 6, 7. That's the whole point. This is giving us a starting place. We probably have at least 2 groups. It might be more like 3, 4, 5 groups. And based on how many groups we just see in terms of sort of little islands here, we might choose a different number. And you can play around with that to compare different groups. Now that I'm thinking 3 to 7 seems realistic, we're going to want to understand what these groups represent. Remember back at the beginning when we saved the original data file? This is why we saved it. Really, we can look at this dendrogram all day long, but what the heck does it really mean? It's not really that clinically intuitive. I'd rather have descriptive statistics, because in my book, if you just know descriptive statistics, you pretty much understand the key information here. So I wrote a little function using my little GitHub thing that's going to allow you to summarize different groups very quickly and easily. This key specify function, what it's going to do is it's going to pull up the data. We gave it the data, the raw data, before any of our transformations on all these different labs. And we can just write a key. If we're making a table here, what's the table going to look like? Well, first we might have some subsections. So we might have demographics, and we might have, then down here we'll have labs. And we can fill this in so that way we have all of the same data in the same locations. This is not a technical thing. This is just organization. So that way we know we're getting information we can understand. Then we're going to say, all right, well, what's the variable name? Well, this is age, this is RDW, this is MCV, this is platelets, so on and so forth. Here's hemoglobin. And the last thing is we'll have rounding digits. How many digits do we want to round to? I'm not going to round age to anything because we're fine with keeping that as a whole number, but I might want to have a couple digits for each of these. Again, this isn't anything technical. This is just for your own understanding. And the reason to do that is that this isn't hard to figure out what kind of table you want to make, but it's hard to get it to go into R easily. So that's why I wrote this function is, and we have this button here, display backup code. What it'll do is it'll write some code for you that you can copy and paste right into R. So that way you can get an easy table yourself set up, formatted the way it needs to work with all the other functions. Trying to make it easy for you because I know I'd make a mistake if it were complex for me. Okay, so now let's say that I look at this dendrogram and I say, I think there's 3 groups here. I want to start with 3 groups. So I'm going to say, I'm going to find 3 groups. I'm going to do this hclust function. It's the same as before, but I'm wrapping it in this cut tree thing. So in other words, select a number of groups equal to k, 3 groups here. Now I have group identities for every individual in the data set. Last thing is then I'm going to create a nice table here. And this is another function that I wrote using that GitHub function. And I'll give it the raw data. I'll give it that key we just wrote. I'll give it the group identities that we just calculated. And I would like it to describe the different groups for me and it's going to give me real simple descriptive statistics. So this is the average, and this is a 95% confidence interval. In other words, how precise is the average for the different groups? So here we have a group that's a 68 on average, a group that's 48 on average, and a group that's 65 on average. Looks like group one is older and group three is older. Group two is a bit younger. We can also talk about these labs. Looks like group one has a high RDW relative to group two and group three. They also have lower platelets than groups two or three. So really, when I'm looking at this, I'm thinking to myself, group one, I'm worried about them. They seem like they might be on the sick side compared to group three, which is also older, but they seem to be a little bit better off. That's the whole idea. We can switch this up. We can say, maybe I just want to look at two groups, run the same thing again, see what we get. Now we have an older group and a younger group, and we can talk about how that intersects with their labs. Older people had lower platelets, for example. That's the whole point. There's no one way to do any of this. We're just trying to get an understanding of what did we find in the data. So that's what I hope you got out of this little video tutorial. Really, cluster analysis is about trying to take something abstract and conceptual and make it more concrete. You probably work with distinct patient groups, and you could name people who represent the kinds of issues you're concerned about. How do you codify that mathematically? Cluster analysis is trying to help simplify that by saying, well, let's look at the data as a guide and then try to correspond that to the information that we have. How can we best understand who the different patients are like and bring it back to basic descriptive statistics rather than abstract regression coefficients that you might accidentally misinterpret anyway? Key thing here. Note that the whole point of this project was to say, I'm worried that some patients are going to be sicker and that's going to cause real problems for them. So we'd really like to look at these different groups in terms of patient prognosis. You know what's not in this analysis? We do not have any information on how the patients did. That was intentional. All of your outcomes you want to leave out of the principal components analysis and the cluster analysis. And that is the whole point. Because now if we have different groups, whether we pick two groups or three groups, however many groups we think are clinically meaningful, then we can compare them in terms of the outcome. The goal of this is what we call hypothesis development, to say who should we compare to whom? Who did we really collect data on? And importantly, if we're testing a hypothesis, we don't want our primary outcome in the data set that we use to generate the hypothesis to begin with, because otherwise that'd be circular. We would know that the people who have the most distinct differences correspond to the outcome. And that was the whole point. We'd like to test the hypothesis that our clinically distinct groups are actually relevant to the conclusions we would like to draw. So that's the idea here. You can include as much data as you like or as little data as you like. You can include as many groups as you think are important or as few groups as you think are important. Really, that's the whole goal, is to try to say, how can we understand what's going on without having to make it so abstract? Can we bring it back to the clinic? And that's why I love cluster analysis. There are some data processing steps depending on if you have issues like skew in the data or missing data. Fortunately, principal components analysis can help summarize the data in a much simpler way, highlight the different trends, and be a little bit more robust to problems with missing data, at least so long as you don't have a systematic bias in who's missing. That's the idea. Hopefully, this helps give you some guidance about how to think about things in the big picture. Of course, there's no one way to do anything. This is just a way that I have found especially practical, at least in my own work. That's all I got today, but thank you so much for joining me. And if you need anything else, you know where to find me.